In this video, we are going to discuss the reactions of imines and enamines. So these are really important functional groups. You'll see them a lot in biochemistry. So you want to be familiar with how these work, how they're made, um, and the mechanisms involved in their formation. So in general, let's start with imines here first. All right, let's start with imines. Anytime you see an aldehyde or a ketone, anytime you see this, you need to, in the presence of a primary amine, you need to think imine, right? You need to think imine. So you want to remember this. This is going to come up so many times, not only in this class, but in your biochemistry classes. The biochemists often call these Schiff bases. So if you ever hear the term a Schiff base, they're talking about an imine. So these are the same thing, right? So these two terms are used interchangeably. But again, you want to remember this. Do not forget this. So that you don't forget, what you should do is you should put a heart right here. You should put my name in the middle of that heart. You can add it to the collection of these drawings that you already have. I know you have so many of them, but you want to keep these reactions here in mind, right? They're very, very powerful. You're gonna see them come up quite a bit. And I don't know how many times I see students and I say, "This, I don't know how this reaction works." I say, "Well, what do you have? An aldehyde? What else do you have? Primary amine? Anything?" And then they're like, "No." It's like, you're just breaking my heart, right? You're just breaking my heart. So don't break my heart. Remember this. Remember, these two things come together to form imines. So let's think about that process. Let's think about those reactions. So let's say that we have a ketone here in the presence of a primary amine. We're going to need some mild acid in this reaction also to facilitate this transformation. And what will happen is, you can imagine the chemistry that's going to happen. I think we've done this so many times already. You can imagine what's going to happen. This is going to attack. It's going to come up. It's going to get protonated, right? So I think you can kind of walk through that mechanism. But ultimately, what we're going to end up generating here is what we would call a carbonyl amine, right? So we would end up with this here, right? So after, and actually just to simplify this a little bit so that we can see exactly here, right? So this is what we'd end up with. But the truth is that the reaction doesn't stop here. This is just an intermediate, and this intermediate is what we call a carbonyl amine. So there's a carbon, so there's carbon, all for alcohol, and amine. But this reaction doesn't stop here. What happens very quickly here is that we end up losing water, right? We lose water very quickly, and what we end up forming here is what we call an imine. We end up forming what we call an imine. So an imine is basically a carbon-nitrogen double bond, and this is going to be the basis of what we're talking about, okay? Now, but in its simplest form, without even knowing the mechanism, we can try to figure out what's going to happen here. Because all you really have to do is imagine taking this nitrogen and putting it where the oxygen is, right? And then getting rid of your hydrogens. So if you put that nitrogen there, well, there it is. It's right there. So it's just a matter of just putting it right there, get rid of your hydrogens. But you do need to know the mechanism, and we're going to go through that mechanism right now. But in the simplest form, if you're just trying to do a quick reaction, you can see that. You simply put the nitrogen there. So why don't you try it with this one? Let's give this a shot. If I asked you to give me the product of this reaction, go ahead and do this. You can pause the video. And see if you can figure out the product. Go ahead, do that. All right, so if you pause the video, Hopefully you got this. You realize that all you have to do is get this nitrogen and put it where the oxygen is and eliminate the hydrogens. So we'd end up with this. And the byproduct here would be water. That would be a byproduct. All right, so let's go ahead and go through this mechanism. Let's make sure we understand how this reaction works, um, and then and how we're getting to the product here. So again, don't worry about what you don't know, worry about what you do know, and use it to the best of your ability. We have this NH2CH3. What do you think that is? Nucleophile, right? So that's going to be a good nucleophile. So it's going to attack where? Yeah, it's going to attack the carbonyl carbon. So these electrons are going to come, attack that carbon, bond has to break, those electrons go there. We end up with this. All right, so that's what we end up with. And I think we can see basically the first step here was nucleophilic attack. So nothing new here, right? We've been doing this for a while. Now, if we look at this, what we have here where it says, okay, well, the oxygen doesn't want to be negative and the nitrogen doesn't want to be positive, they would both prefer to be neutral, right? So what's going to happen here? Well, it's going to be a proton transfer, right? So this is going to come, take that proton, those go there, back to the nitrogen, and what we'll see is that we end up making both, getting rid of our charges and making both of the atoms neutral, right? So now it's neutral. So we see that basically this next step here was a simple proton transfer. All right, so now if we ask ourselves, well, okay, we know what we have to get to, right? We have to get to this product right here, right? And well, if we look at it, Dora the Explorer, what is here that is not in the product, right? Where is it? What is at the step that we just finished that's not in the product? Hopefully you realize that it's this OH here that is not in the product. Well, then we have to turn that into a good leaving group. Well, how do we turn OH into a good leaving group? If only we had an acid. Oh, wait, we do have an acid. We have mild acid in this reaction. So I'm just going to use HA, right, for mild acid here. So what we're going to do here is we're going to protonate it. We're going to protonate this oxygen so that we can turn it into a good leaving group. So we'll get to this here. All right, so there we go, right? So we're made it a good leaving group. Now you realize, okay, well now it just needs a little push, right? It guys needs a little push to kick it off because ultimately what we just did right here is we did a protonation. So now we just need a little push to kick it off. So at that point, who's going to push? Who do you think is going to push? Yeah, it's going to be the nitrogen. We have to form a nitrogen-carbon double bond. So these electrons are going to come here, form a bond. You form a bond to that carbon, you better break a bond. We lose the water, right? So we end up generating this here. Right, so we now have a nitrogen-carbon double bond. So we're almost there, right? We're almost there. We did a deprotonation step. So we're almost to our product. We lost the water, right? So the water came out, right? So here's the water, check. So if we balance this out now, here's our conjugate base. Last step is going to be to do what? Yeah, we got to deprotonate because we know in the product that there's no hydrogen on that nitrogen. So this is going to come, take that proton, that goes there, and we get to our product here. Okay, so with that said, this is the mechanism of that reaction. Now, the interesting thing is if we look at this and we look at these steps here, the last step was deprotonation. But if we just look at all of the steps, oh, and this one, I need to correct this. This was not deprotonation. This was elimination because we eliminated water, right? But again, reactions that is not anything that we're not familiar with. The first step was nucleophilic attack. The second step was proton transfer. Then we protonated to turn it into a good leaving group. We eliminated it, and then we deprotonated it. So did we learn anything new? No, we didn't, right? No, we didn't. But realize that because a lot of this is a lot of proton transfer type of reactions, that this reaction goes forward, this is true, but it also goes backwards, right? It also goes backwards. So it's under constant equilibrium, it's going forwards and backwards, which means that you should know this mechanism forward, but you should also know the mechanism backwards. So I always say know this mechanism forwards, backwards, and in your sleep, right? So, but with that said, since this reaction is reversible, then how is it that we can drive the reaction towards product, right? So how can we drive the reaction towards the formation of our imine? So think about this and then pause the video and click your answer. What is something that you can do to drive the reaction towards product formation? So just think about it, pause the video, and then click what would be the best answers here. All right, so hopefully you realize that we can take advantage of Le Chatelier's principle, right? And we can take advantage of Le Chatelier's principle by eliminating water, right? If we remove water, right, then it's going to push the equilibrium towards the products. And we know how to remove water. If you were in the lab, you remember how to do this. There were several different ways to do this. One way was using anhydrous sodium sulfate, right? This is that salt that you would add that you keep asking your TAs, is this enough? Is this enough, right? And you know that the purpose was to absorb water. It would clump, right? And then your book also mentions another apparatus called a Dean Stark apparatus. It's a piece of glassware that will allow you to eliminate water from a reaction as it's being produced. So again, if you do that, you can push the equilibrium towards the product formation there. So there's ways to control that. All right, so this is imine formation, right? So we just talked about that mechanism and how to form an imine. So now let's talk about the enamine, right? Let's talk about enamine. So when it comes to enamine, it's the same foundational concepts, right? Same foundational concepts. The difference is that in this case, what we're going to do is we're going to react an aldehyde or a ketone. But not in the presence of a primary amine, in the presence of a secondary amine. And anytime you see this, you should be thinking enamine, right? You should be thinking enamine. So again, so that you do not forget, this is another powerful reaction. So that you don't forget, we're going to add another heart here with my name in it so that you can know that you're supposed to love this, right? You're supposed to love this reaction. And so let's see how this works here. So if we do this, let's say that we have this ketone here, and I'm going to react it with now a secondary amine, so 2 R groups, and I still need a mild acid. What we're going to end up generating, we're still going to end up generating that carbonyl amine, so that doesn't change, right? The general mechanism is very similar, right? A lot of the steps are going to be the same here. So we end up generating this carbonyl amine. But the difference is that we don't end up forming an imine, but we form an enamine. So we're still going to lose water here, right? We're still going to lose water, but we end up generating an enamine. So something that looks like this, right? So ene for alkene, amine for amine. So this is what we end up generating here. We end up generating an enamine. So again, anytime you see an aldehyde or a ketone in the presence of a secondary amine, you should be thinking enamine. All right. Now let's go ahead and go through that mechanism. I think you'll realize that the mechanism is pretty similar. right? Pretty similar to the imine formation, but with just a small few differences. So with that said, if we were to push our electrons here, right? So this nitrogen is going to come and attack this carbon. We form a bond to that carbon. You better break a bond so those electrons go up to oxygen. We end up generating this. This is what we end up generating here. Now, so from here, again, I think we can predict what just happened here. We just did a nucleophilic attack. So nothing different here. We just did a nucleophilic attack. So then if we keep thinking about it again, does the oxygen want to be negative? Nope. Does the nitrogen want to be positive? Nope. So what can happen? Very good. A proton transfer can happen. So those electrons go there. This can go here. Now the truth is the proton transfer can come from many different sources. It might come from within the same molecule. It might come from a different molecule that looks just like that one that's in the reaction flask, or just some other type of basic moiety, right? So, but the point is that a proton does get transferred. So here's the carbonyl amine that we ended up generating. But now keep in mind, if we look at this again here, what is here in this intermediate that's not in the product, right? What's in the intermediate that's not in the product? And we see that it's the OH. It's the OH. So we already know how to turn that into a good leaving group. We have a mild acid present here. So we can push our electrons here. So we're going to take that proton, and the whole point of that is to turn that OH into a good leaving group. We've been doing that since organic 1. All right, so there we go. We turn it into a good leaving group. So all it needs now is a little push, right? It just needs a little push. So if you notice, the process hasn't changed so much from the previous example, because we started off with a nucleophilic attack with the imine, and we did a proton transfer, so that stayed the same also. And then we did a protonation to turn it into a good leaving group. So nothing's changed so far. And you can imagine that we're going to eliminate the OH group because it needs a little push. This is going to come here to form a nitrogen carbon double bond, and then that's going to leave. So we end up with this here. All right, we end up with this. Now, the last part here is, well, this nitrogen has a positive charge, and in the product it shouldn't be. It should just be a single bond to Nr2. So this is where it differs because we were fine here. We did an elimination, but this is where it's going to differ because we need to eliminate this hydrogen because this hydrogen here is not in the product. So what's going to happen here is that the conjugate base is going to be responsible for coming to take that proton, right? We form a bond to that proton, better break one. This comes here to form the carbon-carbon double bond, and then these electrons go back to nitrogen, right? So this is basically gets us to our product, but essentially it did so through a deprotonation step. So again, if we look at the process here, nothing that should surprise us. We did a nucleophilic attack, followed by a proton transfer, followed by a protonation. Then an elimination, we turned after the protonating the OH and turned it into a good leaving group, we kicked it off, and then we deprotonated the alpha carbon so that we can generate our double bond, right? Now this is, again, notice that we lost water, right? So at this stage over here, we lost water. So water is a byproduct. And this reaction is also reversible. Just like the imine reactions, these reactions are reversible, which means that you should know this mechanism backwards, forwards, and in your sleep, right? And the same process occurs here, right? We can push the equilibrium towards product formation by taking advantage of Le Chatelier's principle and eliminating the water. If we eliminate water, we push the reaction towards product, and we can do that with anhydrous sodium sulfate, or we can also do this with a Dean-Stark type of apparatus. All right, so how about this? So remember I told you the reaction is reversible. So the same truth is that if we were to, that the reaction can go in the opposite direction. If we add water, we can drive it back towards the starting materials. So how about this? I'm going to give you two problems. Why don't you give me the products and the mechanisms that would be generated? So remember, if the reactions are reversible, this is why you need to know the mechanism backwards, forwards, and in your sleep. So now let's start with the imine and treat this with H3O plus, which is basically acid in water. So we're adding more water here. Give me the mechanism and the product, and then do the same thing for this. All right, take this one and give me the mechanism and the products. And if you do so, go ahead and just take a picture of it, send it to me, and I can tell you how well you did, right? All right, guys, until next time.